So anyway, in light of the pilot project presentation, I thought it would be useful just to have kind of sort of a short discussion on some experimental methods. Now, this is sort of a way to get you thinking. One thing I think that has kind of happened as a result of sort of the dominance of machine learning and neural network techniques is that Neuro dominant conference, you don't see a wide variety in how things are evaluated. It's really the traditional machine learning measurements still sort of dominant. And there's nothing wrong with that. But as we start to look at things that have a symbolic component, maybe use some algorithms beyond your training algorithm, then it makes sense to want to look at some different things. So first to kind of start with is machine learning evaluations themselves. Of course, we're all familiar with the standard things, precision recall, accuracy, F1, but what should you do if you want to go beyond just comparing with the state of the art or the other common models out there? What are some things that you can do? So first is, accuracy. So accuracy is not my favorite measure in terms of giving you insight into understanding how something works, but it gives you sort of this overall snapshot. And accuracy and the way it's measured, they're coming up more and more when these things deal with the intersection between perception and reasoning, because oftentimes, as you saw in some of these lectures, the cases were essentially trying to tackle some kind of multi-class problem where there's a relationship among classes. But going and looking at, hey, how do these results change? Would maybe add some, neuro symbolic or extra thing to it, and getting an understanding of how it improves. This is sort of the point here, looking at this example from a recent paper. So looking at precision and recall, so these are, tried and true. Every undergrad learns about them. First thing is, one useful thing with precision and recall is really kind of the standard for looking at individual classes. But when you look at individual classes and you examine precision and recall, you really should think about and also state what is the split of the classes. So if I'm getting 0.4 precision and that class represents 1/100th of the data set, it may actually be quite good. It's likely something that's tough to predict. What happens often with accuracy measures is they sometimes hide the results of the minority class. And so we want to fully understand that at times. Understanding the split of the data is an important factor when you look at these individual metrics. The other thing that I'm seeing actually a lot more of in the machine learning community is good thing are ablations. And we'll actually see some ablations in the papers on perhaps as well. Here is one of my older papers, the feature-based approach. We categorize the different features in that the machine learning model is using. And each of these sets of bars is when we remove one of those categories. This is telling us the impact. The bars here that here string, we see the impact of that feature. And when you write about your results, there's actually interesting things to note. So for example, out of all of these, we have for recall, when you remove the social network features, the recall drops quite a bit. The precision doesn't really change a whole lot when you do that. So this is telling us that these social networking features, in this use case, we're finding new items that could be properly classified that wouldn't have happened otherwise if you didn't have these features. When I put them out, that recall drops a lot. And you can have similar comments about precision and stuff like that. And so this is very nice set of results because it really tells you how things are contributing to overall performance. And in the discussion part of the experiment, it gives you something to write about. And this is something a lot of students really struggle with is they'll do the experiments and they'll say, look, I got great results. And then they go write it up and beyond the figure, they say, we've got great results. See figure 1, and we were better than the other approaches. But that doesn't really tell you. You want to dig into it more. You want to understand what are some of the things that drove the approach. The better ablation can use to find. Now here, with this feature paper, we've laid different features. Now there's nothing saying it has to be the feature you need to ablate. And if you remember, some of the ABL authors, in one of their papers, they did it where they actually ablated components of it. In some of the CGRAPH papers I've been reading lately, they would do ablation by changing out part of the pipeline. So we'll have something like, hey, here's the object detector, this is the visual recognition piece. We use our fancy super duper CLM that works well with the rest of it. Here's what happens to be ablated and look like something standard. And you see the results change. So rock curves aren't as easy. Yeah, go ahead. It means you're taking something out. You're ablating. So yeah, and that's why it says we moved here. So seeing when numbers from here drop to there, that's what's important. So, yeah, so ablation normally, so you could think of something like, maybe I have some, like, if you looked at anything on like symbolic progression, something like that last year when I taught that, there's this extra step where they optimize the constants at the end, okay? You can still use the result without optimizing the constants. But if you do it, you get better results. And that's some example of something you want to ablate. You can also ablate, again, by saying that we developed a component here that works extra good. Think about, well, when someone says, why do you waste time doing it? You're just trying to fill up the paper. What happens if you put in some standard thing you got off the hugging book? And that's another problem. That's still an ablation, even though there's still a component. Other questions? But this is like a really great way to improve the quality of the paper because you just learn so much from that and it gives you a great part of the narrative. And when you think of it, when you're writing a paper, the story is always something like, we got better results because we've got this great insight. And usually it starts, you talk about, it's like loss functions, with architecture, whatever, right? And you describe all that, and then you say, then I ran this experiment, and boom, everything's better. But if you have a complicated system where there's multiple components, you want to tease it apart. And so that each of those components standard, this kind of gives you that. And it saves a lot of review of comments. We'll take it for stuff. So rock curves, I use rock curves for certain applications that they're considered the standard evaluation, but I think unless you're in something very specific, like we did some biology stuff lately in the lab, with these star charts, you don't want to have them just by themselves because one issue with rock curves or AUPRC is it doesn't always communicate the importance of all the results. So for example, here you might argue, well, this part of the rock curve here looks really bad, and it does. So maybe our application really cares about this part of the rock curve over here where it does well. But the rock curve is really communicating more than anything else is this notion of parameter sensitivity. And this is something that I've noticed, this idea of parameter sensitivity in actually machine learning context. You probably think of it as hyperparameter sensitivity. It's not, we're not talking about learned parameters. This is something that used to be like really common in AI, particularly around things like genetic algorithms and stuff like that. And the reason why that was important is there used to be a lot of discussion about, quote, magic numbers, where I have my algorithm and I have the hyperparameters set just right where it gets the results that are in my paper. And then what you want to do with parameter sensitivity is show that your results are not overly sensitive to parameters. I think the rock curves are essentially a case of doing that because we're varying the confidence level and we show that, hey, this thing, performs well, regardless of where I put that confidence. And I'm getting the appropriate trade-off between sensitivity and sensitivity. The other thing that I've seen emerge a lot in machine learning lately is then do a rock curve or other evaluations on both your training and your test set. And I think this is a really nice idea because at first it may seem like, well, who cares about metrics on your training data? And I would agree by itself, maybe not super important, but when you have both that on the training data and the test data together, right away you can get a feel for how much is overfitting on your training data. Especially if you're comparing multiple algorithms, another interesting result. I might have an algorithm that gives me, area under the curve of like 0.9 on test. Maybe it drops like a rock, when I go to the test data. And maybe I have something where it's a little less, but it's consistent across both data sets. The other thing, though, about training data, particularly if you are in something that's either like outside of computer science or you're in the area of computer science or you're actually just studying something, you can think of this is results on the training data is almost like looking at model fit. So if I have an empirical result in some other field like physics or chemistry, right? And I did a bunch of experiments and I draw a regression line, I'm going to do that R squared value out of the regression line on the only data I have. There's no training and test data. I didn't make a separate data set to train my regression model and see how well it fits. The point of the part of the point of the paper is to see, hey, there's a model that can model this. The training data result may be interesting in its own right. Where I see this most often in computer science, I see it in like things that relate to social science, social media analysis, especially if you're kind of getting into stuff where like a psychologist or a sociologist is involved, as well as biology and medicine. So runtime. Runtime is one of these things that doesn't get discussed a whole lot, but actually is quite important for a couple of reasons. In fact, I would even argue that probably one of the biggest limitations of LLMs right now is actually due to computational complexity. And that's because the context window, your computations with your large language model are going to be quadratic in terms of it. And that's what we do in text. People widely use it. So first thing is, if you have any kind of algorithm that's sort of beyond standard gradient descent, you can have some kind of statement about the complexity. And I think it's worth making. You don't always need to improve the proof, but you can talk about some aspect of that algorithm. So for example, I could talk about if I have some operator here, this operator converges. I don't have a good theoretical result about the conversion, but I can talk about the time complexity for one iteration. And even here, I have the one iteration the size of K squared multiplied by CHK, and they say CHK is bound time it takes to check, something about, if this formula is true. So notice the time to check if a given formula is true could vary widely based on how big the formula is, how complicated it is, and all that. I kind of say, hey, this isn't the point I'm trying to make. Maybe I have a case where the formulas are all easy, or I have some fancy algorithm that takes care of this for me very rapidly. My contribution isn't about this. I can keep that as part of the complexity result. So plotting runtime, this is also a nice thing to do especially if you're dealing with data with an algorithm where you could easily vary the amount of data you're putting through. You can easily verify your theoretical results about computational complexity just by creating a simple regression line and showing that it fits the data. In particular, when part of the paper you're trying to get a point across about scalability, like this is just a nice thing to do. And another thing about this is from a review perspective, saying that, hey, we got, a sublinear time trend, but the input is not that sublinear just because I kind of look at it and it seems that way. You actually have a little bit of a statement there aside. Right away, that's communicating to the reviewers that, wow, these guys kind of nailed down their stuff. And honestly, I think it is important because it's really easy to just say something looks like a certain shape without having any kind of quantification in any way. The other thing that's interesting is, and this comes up in a lot of contexts in combinative force and logic, is this notion of an anytime algorithm. So maybe if I want to run this algorithm and I want a sound and complete result, it's going to take double exponential time or something. But while it's running, it's spitting out results. And those results may be very precise, and I don't know if I got all the answers out of it. It could be something like, hey, I have a bound on probability. And as it runs and runs, that bound collapses, collapses, and collapses. And so sometimes you find an anytime algorithm, and even though if you would let it run to completion, it would take like 100 years, if you run it for an hour, it produces a bunch of useless stuff. And this is kind of having results about this, looking at metrics that view performance, accuracy, anomaly detections comes up a bit, over the amount of time this thing ran, is a really nice result to have. And sometimes you may find some initial algorithmic idea you had that you discarded because you completely solved the problem can actually be included in your report as an anytime algorithm. All right. So the next bit deals with example logic output. So when you deal with something where logical sentences are being produced, this is a great opportunity to highlight an aspect of your system because now you can say, hey, you promised an explanation. This is kind of what it looks like. And so one way to do this, so here is some paper of mine that we did learning and causality. And so we actually have little tables like this where we put the rule preconditions, which is supposed to be what's saying in that section of the rule itself. Now, we could do this without a lot of extra text because we had a table earlier in the paper and we said, hey, here are some of the predicates that we use in the paper and here's what they mean in English. If you don't do this up front, then you need to have an English language explanation for each thing that you provide. But again, this has like a lot of power to it because it communicates to the reader, this is what it produced. Here are some examples that the human can understand and they're interesting. And maybe you can also say, why they're interesting, especially if you have a domain expert. So justifying your own metrics. So this one is really quite important because we see this a lot in other disciplines, and I think it becomes really important in computer science, especially when you get into more applied work. One thing I found with running a company is the traditional machine learning metrics. We had a supervised model that was deployed, and the traditional machine learning metrics weren't as relevant for our use case. They were interesting, but what really mattered were taking versions of machine learning metrics and instantiating them with the workflows that our customers need. And this is the same kind of mindset you should have for just about any heavy application data. And that's what I'm saying here. So a while back, we had a really unique paper about an algorithm to locate missing persons. And you see here, we had a fraction of the area search. So the algorithm would essentially return a bounding box where the search that would be smaller than the look at otherwise. And the area search, the domain experts also said, hey, if you have a dog, you actually get more bang for your buck because the dog sense of smell. They don't have to go everywhere. They have to sense. They're going to go off and find something effectively in the area you need to look at. And so we're able to, based on that domain knowledge, to develop metrics for both without a dog and with a dog, and then epsilon is just the hyperparameter from the algorithm. So that's a totally made-up metric, but we justified it, we motivated it. So we had to have all that in the paper, but it was, effective in showing that the results were good. The other one was, when I talked about this in the abduction class, when we did geospatial abduction back in 2011, we looked at metrics that were not typical machine learning things, but rather we had, hey, you have locations on the ground, how far away, or what is the number of locations that were within half a kilometer from an actual weapons cache. And then to go along with that is what is the mean size of the solution. So we could, so doing this for multiple data sets, again, another domain specific thing. Another thing that you can also think of as a self-defined metric is actually using your objective function. And using the objective function actually is quite a common thing in a lot of combinatorics where I have an objective function, I'm trying to minimize or maximize it, maybe subject to some constraints. And my whole paper is a story about either heuristics or, formal methods that can allow me to perform a lot better. And so this is what we did here. We're moving this charge based on popularity, a metric we defined ourselves, what was used in the literature. And it was NP hard to optimize this exactly, but we could show that our method outperformed other ones. And then we did this other efficiency thing that gave us a little more improvement. And so this is just purely based on the optimization criteria. And that's a totally fine thing to do, especially, if you're doing something more combinatoric where you have maybe the results of perception, making a decision on top of it. And of course, a lot of combinatorial stuff underlies various approaches and logic. So anyway, just wanted to give that a quick idea to maybe help you guys. Any questions on it?